So far we have talked about the linear vector spaces and the Hilbert spaces, how Hilbert spaces are defined. In this lecture we are going to talk about the basis vectors of the linear vector space. Again, the basis vector set actually belongs to the linear vector space, and linear vector space is the Hilbert space is a specific kind of linear vector space, and which follows specific rules and specific conditions. In this lecture we are going to talk about the basis vectors of linear vector space. Again, it's obviously not about the Hilbert space, but it is kind of about the Hilbert space as well. So there is a definition written on the board: linearly independent vectors, a set of vectors, which mean to say that this set of vectors phi I, this set of vectors belongs to the linear vector space. So this set of vectors, all the vectors belongs to this set also belongs to the linear vector space. So it is basically a subset, and again it is the chosen vectors in this set are arbitrary vectors, not specific vectors. This set can be consisting of any vectors. It just has to be linearly independent. It has to satisfy the condition of linearly independent vectors. So what is the condition? So a set of vectors phi I that belongs to the linear vector space for all the vectors belonging to phi I, which is linearly independent, Li linearly independent vectors set, following is true for all vectors belonging to this set. This following condition is true, and if the following condition is true, we call all these vectors that belongs to this set, this subset, linearly independent of each other. So let's look at the condition. So I belongs to 1 to n. So for all vectors belonging to this subset of vector space, summation I equals to 1 to n, ai phi I equals to 0, since phi I the vectors are not equal to 0. So basically every vector has specific length. It is not a null vector. Every vector belonging to this vector, this subset is not null vector. So they are not 0 equals to 0, basically to say. Thus there is all, that mean to say, this condition to be true, we have to put every ai that obviously that forms this linear combination. So this is just a linear combination, and it also can be expanded as a1 phi 1 plus a2 phi 2 plus a3 phi 3 and so on. So this is going to be to a n phi n, and this equals to 0. The above, this is called the linear combination of such vectors. So such vectors, which vectors? Linearly independent vectors. The linear combination of all such vectors, linearly independent vectors, is equal to 0, and all these vectors are linearly independent of each other. So all these vectors are linearly independent of each other. So you cannot write a linear combination which does not satisfy this kind of condition. So all these vectors are linearly independent, basically to say. And here I have shown that this is a vector space where belongs to all the vectors that belongs. This is a phi cluster, this is psi cluster, and this is chi cluster, and there are other vectors cluster that belongs to this vector space, and there exists a subset phi I. It is arbitrary, so you can arbitrarily choose whatever vectors you want to choose. Just all these vectors needs to satisfy this condition. Okay, so the subset phi I and for that all these vectors to be linearly independent, this condition must be true, or it should be followed. So these are the linearly independent vectors. Again, we are not talking about the basis vectors. Okay, so now let's understand what it means by saying that these vectors are linearly independent vectors. Later on we will discuss about the basis vectors are basically nothing but the linearly independent vectors, the maximum linearly independent vectors that belongs to this vector space. Okay, so here you can see the Cartesian coordinate system. For this vector, this vector, this vector, all these three vectors are actually perpendicular to each other. So this vector has nothing to do with this vector has nothing to do with the shadow of the dot product of this vector and this vector is 0, right? The dot product of this vector and this vector is 0. So there is no component of k vector that that actually comes here, right? There is no component of I vector that comes here, or it puts a shadow on this vector. So we cannot write I vector in terms of I and k vector. We cannot write k vector in terms of I and j vector. So basically there exists no such AI for all these three vectors. So in 3 dimensions, dimensions are 3, so there are only 3 linearly independent vectors, maximum 3 linearly independent vectors. That's why they are called the 3-dimensional vector space. Here I have represented the same thing for spherical coordinate system. So where we are saying that these vectors need not to be specific vectors, they can be any other set, there can be any other set that belongs to the linear vector space. So here is the other set of vectors r, phi and r, theta and phi. These are spherical coordinate system. This is called the spherical coordinate system, and these are unit vectors of spherical coordinate systems. So if these are the linearly independent vectors, so these vectors r, theta and phi are also linearly independent vectors. There is no relation between all these 3 vectors. You can see, although here that this r vector is represented in this direction, so r vector is represented like this, but theta vector, this is basically the theta vector. So this theta vector is something like represented as this, the angle made by this r vector with respect to this z axis, g axis, and here the angle made by this same vector. So this vector is just a mirror image. You can see the mirror image here. So there is some if you consider a plane that is cutting the sphere in this manner, so in this manner, then this sphere, this plane is making a phi angle with this x axis, the angles that all these planes are making with each other. For example, that you have this plane is making a 90-degree angle with this I vector, and so this plane j and I plane is making a 90-degree angle with k vector. So every plane that exists in 3 dimension that is making a 90-degree angle with other vector that is left. Here is ai and phi I, that is equals to relation. So this relation is also followed by this these ijk, and also followed by the r theta phi. So by this we can understand the linearly independent vector, what it mean by linearly independent vectors. So this condition where the I and dot product of I and j is basically to say that its I and j dot product is 0, this condition is orthogonality. We will discuss this condition later on. After we are done with discussion of this linear vector space and the linearly independent vectors, we will discuss the orthogonality of the linearly independent vectors, or basically to say that in generally the vectors, and all these vectors are also defined in this manner. So if two vectors are linearly independent, that means they are orthogonal to each other. Now let's talk about the basis of vector space. A basis of linear vector space is set of vectors that belongs to linear vector space. For that, this is the condition: a maximum number of vectors. So basically, maximum number of vectors. A maximum number of vectors that are linearly independent is called basis vector of linear vector space. So it's nothing, the set is also, still it is every vector that belongs to the set is linearly independent of each other. They are not linearly dependent on each other. So this set needs to be still, every vector that belongs to this set, every vector needs to be linearly independent of every other vector in this set. And the condition for the basis vector is only this one condition here: set a maximum number of vectors. So this phi I, maximum linearly independent vectors, is equals to basis vector of LVS, linear vector space. Okay, so that was the first condition. Now the second condition is to be the basis vector of the linear vector space if the basis vectors span the entire space of space means LVS, linear vector space, then it's said to be a complete set. So what does mean by the span the entire space? Here I have explained the meaning of this one sentence or line. Span the entire space means, this means any vector of linear vector space, this vector space. So it can, the vector can belongs to the psi cluster, the vector can belongs to the phi cluster, the vector can belongs to chi cluster, and any vector, any random vector, any vector of LVS can be written as a linear combination of basis vectors. So here is example I have given. So consider that this vector space is in general n-dimensional vector space. So this vector belongs to this psi cluster. There is a a1 phi1, a2 phi2, and so these vectors are linearly phi1, phi2 and phi n. These vectors are linearly independent vectors, and they belongs to the basis vectors set, since they satisfy this condition that they are a complete set. Any other random vector can be written as the linear combination of all these basis vectors. So for example, to get the full idea of what it means, so here let's take the example of three-dimensional vector space. A vector belongs to three-dimensional vector space, any random vector. It can be written as this 3i plus 4j minus 3k. Here these I, j and k, these vectors are the basis vector for the three-dimensional vector space. And here a1, a2 and an are nothing but some numbers. They can be complex number, and here these numbers are real numbers, of course. So this is literally nothing but saying that any other vector can be written as a linear combination of all these linearly independent vectors, which are basically the basis vectors, which are the maximum vectors maximum linearly independent vectors that belongs to particular vector space, and they are not specifically spatial vectors. These vectors are can be arbitrarily chosen, so they just need to satisfy few conditions. For example, they needs to be linearly independent, and they needs to satisfy one another condition, which is they needs to be they needs to be linearly independent of each other, and there needs to be maximum number of vectors that belongs to that are the linearly independent vectors for that particular vector space. Okay, so here I have explained this very well. If you get the proper idea of what is the basis vector, what does basis vector means, and now here let's talk about the dimensionality of why the three-dimensional vector space is called three-dimensional vector space, because there are three vectors, only three maximum vectors. So even if you change the coordinate system from going from Cartesian coordinate system to spherical coordinate system or cylindrical coordinate system, the maximum linearly independent vectors are only three vectors for three-dimensional vector space. So here it is written as n-dimensional. So since there are n linearly independent vectors that belongs to this vector space, and they satisfy this maximum number of vectors condition, that these vectors are linearly independent, and they also belongs to the LVS linear vector space, and they span the entire space. They basically any vector in the linear any other vector that belongs to the linear vector space can be written as the linear combination of all these n vectors. So that's how they span the entire space. Spanning means any other vector can be written as a linear combination of these n basis vectors. Okay, and dimensionality also comes from the same thing. So if you think about it, the number of maximum number, this maximum number represents the dimension of LVS. How many linearly independent vectors that belongs to this particular vector space. So this number, this maximum number, is actually the dimension of linear vector space, and this maximum number can be, so in generally we treat when we formulating the mathematics for the quantum mechanics, or any mathematical formation, any mathematical theory, or in formulas, we generally use the n dimensions, not particular number. So n can be three-dimensional, n can be four-dimensional, n can be n-dimensional. So it can be anything, right? So let's move towards the dimensionality of the vector space. So now let's talk about the dimension of vector space. The number of vectors, how many number of vectors there is. The number of vectors that span the entire space is called the dimension of vector space. And in other words, you can say that since the basis vectors span the entire space, therefore if the basis vector set is complete set, then they span the entire space. Therefore the maximum number of vectors in basis set is called the dimension of vector space. So now let's understand a little bit about how they span the entire space. So let's consider this there are vectors such as, you cannot imagine, obviously they are not looking like orthogonal to each other, but you can think of x, y and z. You can think of all these vectors written here from phi 1, phi 2, phi 3, phi 4, phi 6, and phi 7 and phi n. All these vectors are orthogonal to each other, which means to say they are perpendicular to each other in some manner. In general sense, you cannot call these vectors they are perpendicular to each other, but you can think of the same condition. Here is the same condition, but again you cannot imagine the four-dimensional space and you cannot imagine the n-dimensional space. So here we are representing the n-dimensional space. So this vector is orthogonal to this vector, and this vector is orthogonal to this vector, and this vector is also orthogonal to this vector. So all these are axes, just like x-axis, z-axis and y-axis in 3 dimensions. You can think of all these vectors are axes. Here you pick any vector that is psi. So this vector have some shadow on this phi vector, have some shadow on this phi 2 vector, phi 3 vector, phi 4, phi n vector. So basically when you say that this vector has some shadow, some portion going into this vector, this vector, this vector, so you basically can write this vector in terms of a1 phi 1, a2 phi 2 and so on, an plus an phi n an or an phi n. So it can be a linear, this psi can be written as a linear combination of all these linearly independent vectors. So this is how n-dimensional vector space looks like. In general, you cannot imagine the how n-dimensional vector space looks like, since our brains are not made for thinking about the how n-dimensional vector space looks like, since we only can interact with this 3-dimensional vector space or the space in general, or space is 3-dimensional and obviously the 4-dimensional space, but we can interact with the 3 dimensions only, and we can imagine 3 dimensions only. So this vector space is n-dimensional vector space, and any vector can be written as a linear combination. Here any vector, let's just say v vector, can be written as a linear combination of j, I and k. So these are unit vectors. So you can also make these vectors unit vectors. You just have to divide these vectors by their norms, and when you divide these vectors by their norm, you will get the normalized vector. So phi will become normalized. So this is what we call normalization. But later on we will discuss normalization, but for currently you have to understand this thing, that this any random vector psi that belongs to this vector space can be written as a linear combination of these vectors. So this is n-dimensional vector space, and this is 3-dimensional vector space. And the n-dimensional vector space, the number n here can be any number. It can be 4th dimensional, it can be 6th dimensional, it can be some other dimensional. Okay, so I hope you get the idea of dimension of vector space. Obviously sometimes it gets very confusing when you study that. Okay, what does spanning means? Span the entire space. Span the entire space means you can write any other vector, random vector in the vector space can be written as a linear combination of these linear vectors, which are the basis vectors. And there are always basis vectors, and they can be chosen arbitrarily. They are not necessarily I, j, k. They can be r, theta, phi unit vectors. They can be r, rho, phi unit vectors for cylindrical coordinate system. So obviously these vectors are not specific vectors, but they need to satisfy the few conditions which we have already discussed, that how a basis vector set forms and how a basis vector set defined. Okay, now we will discuss about the Dirac notation. I think it is important for you to learn a bit about Dirac notation before we get into the idea of orthogonality or the orthonormality or the normalization condition or the orthogonalization condition. So you have to have some basic idea about the Dirac notation, and the Dirac notation was developed by Paul M. Dirac,